Alright, let's answer question 12. What code fragment codes the equivalent circuit if you remove the barrier in the following quantum circuit? So this barrier doesn't do anything because there's only one qubit and there's no other qubits to wait for. The barrier waits for all other operations in the qubits to be done before continuing onward. So we can just disregard it. And I want to focus on the Dirac notation of this. In the second video, I'm going to explain how to find the Dirac notation of this final quantum result. So how would we describe the final quantum result using Dirac notation? And we're going to do all of that with Dirac notation instead of using vectors and matrices. And here we'll do that as well. I think it's important to use the Dirac notation and practice using it because physicists and other people in quantum computation that you work with will be speaking this language and not always using the matrix multiplications and vectors like you may have been practiced from linear algebra. So we need to be able to speak the same language, and this is a good way to practice. The Hadamard gate can be represented as the outer product of all possible options for the basis vectors. With this minus giving the -1 on the right side of the matrix. And so all of that is also multiplied by 1 over root 2, and that's the direct notation for the Hadamard gate. For the T gate, well, this is going to be equal an R phi gate with phi equal to pi over 4. So the R phi gate is a rotation by the Bloch sphere around the z axis, and phi specifies the phase of that rotation. And so here is the R phi gate. We have the 0 outer product with a phase on the 1 that will add a phase to the 1 state whenever applied to the 1 state. And so phi for the T gate is equal to pi force. And there we go. So let's see which of these options gives an equivalent circuit if we were to substitute what it had for, which ones are equivalent. And the way that I like to look at this is the final result is equal to a sequential left multiplication of all the operations. So it's kind of in reverse order. Since we need to left multiply, we'll start with the Hadamard, the T, the Hadamard, and that will be the final result that we'll figure out how to solve concretely in the next video. And so then looking at that way, it looks like they're trying to use S to equal T squared for option A, because the H is the same, and they just substituted S for T squared. Is that the case? Well, S is equal to an R phi rotation of pi halves. And so then that would mean that the square of T would have to equal S. So let's square T, and if we do this quickly, we can say, okay, multiply the first part by itself, and then multiply the two parts together, since we're going to have two of them in the inner parts of this foiling. Then we'll just put a 2 for the coefficient, and then we have the left part first, multiplied by the right part, and then we have the right part multiplied by itself. So that means this will be squared, and this will multiply by itself. And now this is why I like the Dirac notation, because we can easily reduce all these matrix products. We don't have to go make sure we do them all correctly. We can just look at the inner products, cross those out or combine, and then combine like terms, and we stay in the direct product the whole time without ever having to do matrix multiplication. So these inner products here, 0 inner product equals 0, will either be a 0 or a 1, since these are orthogonal vectors. If they're parallel, then it will be a 1 scalar, and if they're orthogonal, then they will be a 0 scalar. And so we know 0 is equal to 0, so that's a 1 scalar, and then this is orthogonal, so that'll be a 0, and this is parallel, so that'll be a 1. So then we don't have to worry about that inner part, and we just worry about what this results to. That resulted down to a 1, so now we just have the outer product of 0. And then e to the I pi over 2 is equal to squared is equal to e2 I pi over 4. And this part will go back to what it was before. So we just squared the phase part, and this will reduce down to 1/2. And there it is. Looks like S to me. So A is the right answer because it correctly substitutes for t squared the S gate. But B, C, or D, what about those? Those could be the right answer. So B looks like it's thinking that whole process is equal to the identity. Well, H squared is equal to the identity since it removes the superposition. It inverts itself, but what about T squared? In order for T squared to be the identity, then T would have to equal T dagger. And that's because, by definition, unitaries, T dagger equals the identity. And so, since that's also to like T inverse, and that means T would have to be its own inverse, and that is not the case. And we'll see that because, this is true. We'll see that's not the case because we would have to take the conjugate transpose of T. So if we took the conjugate transpose of this, then disregarding what happened here or what happened here, we would know that we'd have to transpose and conjugate the e to the I pi over 4 parameter. And in order for it to stay the same, it would have to be the same. So e to the I pi over 4 conjugate would have to equal itself. The e to the I pi over 4 conjugate is equal to e to the negative I pi over 4. So there T is not equal to T dagger, and therefore C is the wrong answer for using T dagger instead of T, and B is the wrong answer because it's not equal to identity. D thinks that Z is equal to T, but Z has a phase parameter for the our phi gate of pi. So e to the I pi is equal to -1, and that's how we get the -1 in the bottom right hand side, but that's not equal to T either. So in the next video, we'll talk about how to figure out the final quantum result of this circuit before the measurement and be able to compare that to others.